All right, great. Well, yeah, thank you for that nice introduction and for the opportunity to describe a little bit about the observational side of gravity here. I know the focus in the summer school has mostly been loop quantum gravity and the theoretical things, but I think it's nice to try to connect to some extent with observation, and I'll talk about this exciting probe of gravitational waves, which may be one way to test at least some features of quantum gravity. Okay, so in this talk, I'll describe a few different topics. So since this isn't a observational summer school, I'll just go over a bit about gravitational wave detectors, kinds of sources they're looking for, and what actually has been found so far in our universe. And then I'll switch over to what we've been learning in terms of the theory of general relativity from performing observational tests with the detections of gravitational waves. I'll spend a fair amount of time describing one feature of the infrared properties of general relativity, namely the gravitational wave memory effect, which I know at least was mentioned in a few talks earlier in this school. And time permitting, I'll discuss a little bit about the future outlook for gravitational wave detections. Okay, so let me just begin by introducing sort of the main players in the gravitational wave detection game. There are two detectors in the US, the LIGO, Hanford, and Livingston detectors. One in Europe, the Virgo detector, and there's a fourth detector, which is nearly in the state where it will begin detecting gravitational waves in the Kamioka mine in Japan. That's the Kagra detector here. The basic principle of gravitational wave detection is relatively straightforward. These are kilometer scale Michelson interferometers. In this schematic here, they're basically just a laser, beam splitter, and two mirrors. And this interferometer is tuned such that initially the arm lengths are equal, so you have destructive interference and no light comes out of the dark port. But if a gravitational wave comes down and impinges on this detector, the proper distance along the two arms will lengthen in the one case and shorten in the other. And this will lead some light to leak out of the interferometer, and this light coming out can be calibrated to a strain. And this is the physical effect that these detectors measure. So the question is, how well do they do this? The sort of common way to quantify this is with this so-called power spectral density of the strain noise. So what does this mean? Well, for the LIGO detectors here, it says that at 100 hertz, the sort of typical strain fluctuation is on the order of a few times 10 to the minus 24. So in terms of physical distances, this means these LIGO and Virgo detectors are measuring distances over the kilometer scale detectors that are about 10 to the minus 19 meters, which in other words is an extremely precise measurement of distance over these kilometer scale detectors. So it's a quite incredible experimental achievement, even if the basic principle of these detectors is relatively simple. Okay, so then there's the question of what are these detectors looking for? And the most familiar sources, those that have been detected by LIGO and Virgo, are these binaries formed of black holes and neutron stars and all sort of possible combinations of the two objects. But while this will be sort of the main focus of my talk, I'd like to just briefly mention that LIGO is looking for a number of other interesting sources. So for example, neutron stars aren't perfectly spherical. They have little bumps, a small mountain, just like a mountain on Earth. And they're rotating extremely fastly, and this produces some monochromatic gravitational waves, which LIGO is actively searching for and has put some interesting constraints on them. There's also searches for just a stochastic background of gravitational waves, primarily produced just by a large number of these compact binaries, but also potentially below this primary astrophysical background, there's a cosmological background lurking, and there's active searches for these gravitational waves. And then there's a number of other kinds of sources, so things that are difficult to model, like if a star explodes, it produces substantial gravitational waves, although they're rather complicated to model, but there's techniques to look for this. There are other, cosmological sources like cosmic strings and various networks of cosmic strings. And there's a number of searches for these. And even there are sets of searches for what I'm describing as, unmodeled things. So if it just looks like there's some additional strain that's coherent between all the detectors, but isn't a known astrophysical source, something that's being modeled, then there are ways that LIGO and Virgo could search for this. So there's always sort of the looking for the unknown and surprises. But the main focus of this talk really will be the compact binaries. So I'd like to dive a little bit more into what are the gravitational waves for these systems and what one can learn from them. So for finding gravitational waves from astrophysical sources, I just mentioned one can, in principle, be completely agnostic in the searches, but it turns out that if you know what you're looking for, it's easier to find it than if you don't. So the most sensitive searches are ones that use templates for the gravitational waves and look for signals of a known morphology. So for binary black hole systems, which will be the focus of this talk, the waves have sort of three characteristic stages, which correspond to different stages in the evolution of this binary. So there's a long, slow period where the two black holes just orbit around one another, and their separation slowly decreases until eventually they come together and merge. And during this slow inspiral process, both the amplitude and the frequency of the waves slowly grows in amplitude and in rate, until finally there's a last plunge. The two black holes come together during this brief merger stage where the emission peaks, and then it exponentially dies away as these two individual black holes settle down into a single black hole plus some perturbations in space-time, which exponentially decay away. So these are the sorts of signals that LIGO looks for. And although I'm just showing one signal from some characteristic system, the precise rate at which this amplitude and frequency grows, and the precise ring down time scale and damping time and so on, these all depend sensitively on the masses and spins of the objects before the merger. So one can actually infer a great deal of information about the astrophysical properties of these sources just from these waveforms. So it's using this sort of inference that LIGO and Virgo has been able to make a sort of first cut of what the population of binary black holes and neutron stars is in the universe. So this plot nicely summarizes it. On the vertical scale here is the mass of the compact objects. So blue objects are black holes, orange objects are neutron stars, and these couple gray objects are things that are difficult to determine if they're black holes or neutron stars just from gravitational wave data alone. So the horizontal scale here doesn't have any significance. It's just to spread out the objects so they're not all clustered together. So each triplet here shows the two initial black holes at the bottom, and then are connected by an arrow to the final black hole that's formed as a product of this merger. And just to give you a sense of how this field is picking up, in 2005, LIGO had its first observing run during which it detected 3 binary black hole systems about a year later, in 2017, LIGO and then briefly Virgo ran for the second observing run of these detectors, during which 7 more binary black holes and the first binary neutron star was detected. And then in 2018, at least for half the year, there was the third observing run. And during this third observing run, now roughly 40 compact objects were discovered, and this was largely due to quite impressive increases in the sensitivity of these detectors, which expanded the range over which they can find these binaries. This happened all just in a period of 6 months. So there are a number of other detections, or I shouldn't say detections, other candidate detections, which haven't been announced yet, but this number is going to very rapidly increase. So this, in other words, is sort of, the state of gravitational wave detection to date. And now I'd like to turn to what one can learn about the theory of general relativity from such detections. So one common way that people motivate this is, why test GR? GR seems to be quite well confirmed even prior to these detections. So one way is to think about the following parameter space, where on the horizontal axis, I have the characteristic mass of the system divided by its characteristic length, which you can think of, say, as a parameter describing how nonlinear or strongly interacting the objects in the system are. And on the vertical scale, I have an inverse length scale, which is the inverse of the curvature of space-time. So sort of the mass scale divided by length cubed to the 1/2 power is an inverse length scale. So when, let's say, prior to the detection of gravitational waves, Einstein's theory was sort of best probed in the solar system by experiments like lunar laser ranging, very precisely measuring the distance and hence also redshift and so on between the Earth and Moon. And the classic experiment like the perihelion precession of Mercury, which of course Einstein in some sense required his theory to recover this observational discrepancy between Newton's theory and the orbit of Mercury. But even going beyond the solar system to some of these more relativistic objects like pairs of neutron stars and orbits around one another, these gravitational wave systems are probing a new area of this parameter space of strength of the gravitational interaction and length scale on which the gravitational interaction is being probed. So simply from a phenomenological viewpoint, it's interesting to confirm that Einstein's theory holds in this region of parameter space, which hadn't really been tested before. As for what can be tested, I think this figure nicely shows that the kinds of length scales that one thinks about, at least for binary black hole systems, on the low end are sort of around the horizon scale of these objects, which is somewhere around tens to hundreds of kilometers, depending on the mass of the black holes in question. But gravitational waves can also do tests of general relativity on quite larger distances, because these gravitational wave events are actually taking place billions of light years away from the Earth, and obviously thus are taking place quite much earlier in the universe's evolution. So one can also look for deviations, or another way of saying it is testing the predictions of general relativity on length scales that are quite long. So these cosmological kinds of length scales. So I think just my personal opinion about this is, if one wants to then attempt to test quantum gravity with gravitational waves, you really need to, you're not going to be probing Planck scale corrections with these systems unless for some reason, Planck scale physics produces some sort of macroscopic effect, either say on the scale of black holes or kilometer scales, or produces some changes on cosmological scales in which, some subtle effects accumulate over, billions of light years. So if, you have these kinds of effects, then you can test quantum gravity. And this obviously limits the kinds of quantum gravitational effects one might test with gravitational waves, but there still are some interesting things which I'll describe in this talk. Okay, so first, let me just describe sort of the tests that have been done with gravitational waves by the LIGO and Virgo collaboration, and then I'll discuss a bit about some exciting tests about the asymptotic structure of space-time that one can do by looking for the gravitational wave memory. So what has been done, I've listed just a subset of all the possible tests of relativity. There are a variety of tests, one which I'm calling excess power, which is sort of an agnostic test, just saying if you subtract off the best fit template, is the residual, what remains, consistent just with your model of noise. And then there's another test sort of looking for any possible extra energy or angular momentum that's radiated that wouldn't be predicted by relativity. Some other tests involve the propagation of gravitational waves. So do they propagate like massless fields and the speed of light? These are questions that LIGO has answered. And then also issues of polarization. So do gravitational waves interact with the detector as, say, a spin-2 field would? Or is it more like a scalar or vector field? These are questions that one can, in principle, probe with gravitational waves. And if you're quite interested in this, there's a number of other tests that I haven't described. They're summarized in some of the reading material that I linked on the webpage for this summer school. Okay, so let me first, to describe these tests, let me just give a very basic statement about some statistics that are used to assess the significance of a detection. So one statistic that's commonly used is the so-called signal-to-noise ratio. And essentially, you can understand this if you take the Fourier transform of your strain signal, h of t, how much the LIGO and Virgo detectors are stretching and squeezing, and you square it and normalize by this noise spectrum, so this U-shaped curve, which represents, how noisy the detectors are. Then essentially, right, what you have is a signal divided by a noise, so hence the name signal to noise. And the total signal to noise is just how much, the signal stands out above the noise spectrum at every frequency. So you sum this up, and this gives you the total signal to noise. That's what the integral here over frequency is doing. And the way to interpret this signal to noise ratio depends on sort of the search that you're using. But if you just had one template and you were looking for one thing, a signal to noise of 3 would mean something like a 3 sigma significant detection. But unfortunately, in these LIGO searches, you often have to use a large number of templates. So there are look elsewhere effects and so on. So you have to raise your threshold to a higher value to actually, say, determine a detection. Okay, so this simplest test that one can do is this so-called residual test. So one looks at what the signal to noise of the best fit template in general relativity is. And then after subtracting this from the data, one produces an upper limit, sort of a 90% confidence level upper limit on what the residual signal to noise is in the detectors. So this doesn't assume, anything about the morphology or properties of the of the excess power just looks to see simply, is there some additional signal that's not properly being modeled in general relativity? And essentially this test then, computes this residual signal to noise and compares it with the GR signal to noise, and then computes a statistic, the p-value, which, in other words, says how likely is it that you would get a residual signal to noise at least this extreme under the hypothesis that general relativity is your correct theory. And as you can see, the smallest likelihood, this blue diamond shape here, is about 0.07. So there's, roughly a 1 in 16 chance or so that you would have a residual signal to noise disallowed under, the hypothesis that GR is correct. And since, about 30 or so events were considered here, this is completely expected that you'd have one event extreme. So as the conclusion that one takes from this is that general relativity is perfectly well, works perfectly well to describe the signals, and there's not really any excess power that is being missed so far. Okay, so these sort of agnostic tests, tend to be useful, but they usually aren't the most sensitive. So it's useful to perform other kinds of tests, which make some additional assumptions and can provide slightly stronger constraints. To do this, it's useful to say a few words about hypothesis testing. This is usually done through the framework of Bayes' theorem, which is just a statement about joint probabilities, that the joint probability of having some realization of the data and having some model theta j that fits it, is equal to these two expressions for the conditional probabilities. So what's nice about Bayes' theorem is, the things that one is usually interested in terms of, understanding, the properties of the parameters, these so-called posterior probability density functions. This posterior probability distribution is somewhat hard to compute, as is the so-called evidence, so the probability for the data given a hypothesis for the model that's being used. These are challenging to compute, but the right-hand side, this so-called likelihood, the probability of the data given your model, and your prior posterior density function, the probability, your a priori probability for these parameters, which is usually assumed to be uniform or agnostic. These are something that are easy to compute. So there are two kinds of tests that are done. One is simply just to compute these posteriors for some model which includes some effects beyond general relativity and put constraints on the parameters of your model. Or there's a second approach, which is to compute these so-called evidence ratios. So if you have two hypotheses, say one in which there's hypothesis one is, the data is described just by general relativity plus some noise, versus hypothesis two, it's described by your other favorite theory of gravity plus some noise. You can then compute this evidence ratio or Bayes factor of the two hypotheses. And just to give you a sense of this, a Bayes factor of 100, or the log 10 of it being 2, is generally considered to be strong evidence for one hypothesis versus the other. Okay, so with this sort of Bayesian framework, one can then perform some other kinds of tests of general relativity. So one of which is this Inspiral merger consistency test. So in this test, it relies on the fact that general relativity basically produces a map for what the final mass and final spin, this is the dimensionless spin of a curved black hole, are, that are formed from two black holes of masses m1 and m2, and two dimensionless spins, chi1 and chi2. So this test then essentially checks the consistency of the prediction of the final mass and spin using the waveform up to a given frequency, so specifically sort of the frequency at which the black holes start plunging towards each other, and then makes an independent estimate, so from both before and both after, and checks the consistency of these estimates. So if for some reason during the merger, some additional mass were radiated from the system that's not predicted by general relativity, you would have a value of this delta m, which is non-zero. So in this test, the value of delta m and delta chi of 0 is the prediction of general relativity. And what's nice about this test is if you say then normalize this deviation in mass or spin by the average mass predicted from both the pre and post merger signals, one can then combine the estimates that one gets, so these credible regions here from all the individual events, and get a much stronger constraint, which is what's shown in this gray region here. So as one can see from combining, on the order of not all the events, but just say the loudest events when one can perform this test, so the 15 or so loudest events, one's getting, say, somewhere around a 10% error on what this delta m is. So in other words, the GR prediction, at least for the mass from these two independent estimates, is accurate to within 10%. So one's beginning to get reasonably tight constraints from this kind of measurement. And this will only get better as more events are detected and combined, because these errors sort of grow with 1 over the square root of the number of events. Okay, so I'd next like to describe a few of these propagation tests. So these are one way in which these propagation tests are performed, at least by the LIGO collaboration, is to try to understand what would happen if there was a modified dispersion relationship. So in other words, instead of having E squared is P squared, as you would for a massless field, what would happen if you had some coefficient A sub alpha times the magnitude of the momentum to some power alpha. So for those of you used to Einstein's summation convention, these are not vectors. This alpha is just some number. So if one has this dispersion relationship, it leads to a change in the phase where you can estimate the order of magnitude of this effect as going like, say, A, the coefficient here, sub alpha, divided by the characteristic energy of a graviton of the characteristic frequencies of binary black hole mergers, so a few hundred hertz. And this, H bar omega, or HF, is sort of PeV scale for the typical binary black hole systems. And then the size of the dephasing basically depends on the ratio of this scale times essentially the number of gravitational wavelengths between the source and the Earth. That's this luminosity distance divided by the gravitational wavelength. So this effect can essentially constrain this parameter to be sort of on the order of 10 to the minus 20 in these somewhat awkward units of pico electron volts to the 2 minus alpha. So just to give sort of a concrete example for alpha equals 0, this would be a dispersion relationship that's E squared equals P squared plus some constant. So one can think of this constant as the mass of the graviton squared in this case. So in other words, this constraint of being 1 times 10 to the minus 20 in units of PeV squared corresponds to constraint on the graviton mass, meaning it must be less than, say, 10 to the minus 22, roughly, in units of EV. So in other words, these propagation type tests have put a very strong constraint on the upper limit for what the maximum mass of a graviton can be. So this is a kind of quantum gravitational effect that one can actually perform with gravitational wave experiments. Another interesting effect that happened as a result of a binary neutron star merger. So there's this gravitational wave event in 2017 on August of the 17th. And what's shown in the bottom is the frequency evolution of the gravitational waves as a function of time. So this is sort of the track that one would expect to see from a binary neutron star merger. And then only 2 seconds later, in the Fermi gamma ray telescope, it noticed this excess of gamma rays. So this is kind of what one would typically see from a weak gamma ray burst. These are the energy scales for the gamma ray photons. So these were co-located in the sky, and the chance that this is a coincidence, that there just happened to be a gamma ray burst unrelated to this gravitational wave detection, is extremely low. So in other words, from this one can put a constraint on how much faster or slower gravitational waves propagate from the speed of light. So for example, if they're emitted at the same time and the 2-second delay was because gravitational waves propagate faster than the speed of light, you can put a constraint on the order of 10 to the minus 15 for the difference between this ratio of the gravitational wave speed and speed of light and 1. And similarly, one can put a lower bound by assuming that there was some delay, so the gamma ray burst actually happened 10 seconds later and light sped up to catch up with the gravitational waves, so it's a bit faster, and this gives you a similar sort of lower constraint. And in the context of some Lorentz violating theories, this improved the constraint by a factor of 10 to the 10, so 10 orders of magnitude. And it also put a number of interesting constraints on classes of modified theories of gravity, where it's assumed, at least to explain some properties of dark energy or cosmological constant, that the propagation speed of gravitational waves and light differs. This was actually one of the stronger constraining effects. So this is another quite interesting constraint that at least in this case in particular, that multi-messenger, so both having electromagnetic radiation and gravitational waves, was able to place. And then one final constraint that I'll mention is that of what the polarization of gravitational waves is. So this test was done in a sort of relatively simple way, in which it was assumed that the gravitational waves, are generated by the source in exactly the same way. They propagate as, any massless field would between the source and the Earth, but they have a different polarization. So the sort of GR hypothesis is that they're a spin-2 field or have a tensor polarization. And it was compared against the hypotheses that they interact with the detector like either a scalar or a vector particle would, so the red or the blue points here. And as one can see, for these individual events, the scalar hypothesis is reasonably disfavored. So, this Bayes log 10 Bayes factor is above 1. So there's, some, it's not definitive, but there's good evidence that the tensor polarization is preferred over the scalar. But what's sort of interesting is, even this in this simple-minded model here, it's hard just to distinguish from the data whether the gravitational waves have a more vector, so spin 1 sort of polarization versus a spin 2 type polarization. So this, I think, is just one interesting example showing what are sort of the limits in terms of tests of general relativity that one can do, that even something that seems like is sort of a naive hypothesis still can't simply be ruled out from the data. Okay, so this is sort of, wraps up what I'd like to say about sort of the tests that have been done. And now I'd like to turn to the subject of these gravitational wave memory effects and the possibility of constraining and learning about the asymptotic structure of space-time from gravitational wave measurements. Okay, so to motivate this, I'll again show a new sort of parameter space. So I'll to show why this is sort of an interesting thing to constrain and why this is something unique to gravitational waves. So I have essentially the same horizontal axis, this sense of non-linearity, although I've now included factors of G and C just for the moment. And on this vertical axis, I'm showing the gravitational wave luminosity. And I'm showing it in units of the so-called Planck luminosity, which is the unique luminosity that you can construct from Planck's constant, Newton's constant G, and the speed of light c. And as you can see, it's an enormous luminosity, 10 to the 52 watts. And it also happens to be, one can think of it as a quantum gravitational luminosity, even though each bar doesn't actually appear in this, because it is basically, what happens if you radiate a Planck mass in a Planck time. Okay, so a system like Mercury and the Sun, or the perihelion precession of Mercury, the system is a quite weak gravitational wave emitter. And it emits, actually roughly about a watt of power, so weaker than your average desk lamp, say, in gravitational waves. So not surprisingly, no gravitational wave phenomena were ever detected from Mercury and the Sun. However, where gravitational waves were first detected was from these double pulsar systems due to the slow decay of the orbit over decades. And these systems are much more luminous. So in terms of their Planck luminosity, it still looks small, but they're radiating a luminosity in gravitational waves, which is roughly equivalent to the optical luminosity of the Sun. But these gravitational wave systems, like the first event that LIGO and Virgo detected, these are systems that are radiating close to the Planck luminosity. So one will be able to actually probe some of these very strong luminosity effects that just really aren't feasible from other kinds of experiments. So one such strong luminosity effect, which is quite interesting, is this gravitational wave memory effect. So I've sketched schematically what the memory effect is here. Sort of the standard picture of a burst of gravitational waves is it starts without straining the detector, passes by, and then it leaves the detector unstrained. But a burst of waves with memory has some lasting strain, some offset delta H, which endures even after the gravitational waves have passed. So in terms of, say, what this would do to the LIGO and Virgo detector, the waves without memory would cause the detector to stretch and squeeze and to have some light coming out of the interferometer as they pass. But after they pass, the initial and final configurations, 1 and 5, would be the same. However, in this idealized version of LIGO, where it really is, say, a freely falling detector, then after the waves have passed, the detector would remain in some sort of distorted state. It would have one lengthened arm and one shortened arm. and there would be some light coming out of the interferometer. So there is, in principle, an effect that one can measure. And this gravitational wave memory effect is, a prediction of general relativity that is expected for most gravitational wave sources. So why is this? Well, the way in which the memory is computed from astrophysical sources sort of has the following form. There's a part related to what I'm calling changes in conserved quantities, which I'll define more precisely later. But it's basically, the result of what happens when you have scattering of massive objects like black holes and neutron stars on unbound orbits. And then there are two additional terms which are sometimes called hereditary. They depend on the entire past history of the source. And what they depend on is this so-called energy flux per solid angle in massless fields, which sometimes gets called the linear memory. And then a similar term from the effective stress energy per solid angle radiated in gravitational waves. So a system like a supernova in which a very large number of massless or nearly massless particles like neutrinos are emitted asymmetrically from the source, this produces a gravitational wave memory effect. And similarly, there's a gravitational wave memory effect from this asymmetric radiation of the effective stress energy of gravitational waves from a source. So what then does this look like? Well, this first waveform that I've shown here is sort of the one without any memory, where it oscillates around this zero mean line and then settles down to a value 0 at late times. But if one carefully computes the waveform, including all these subtle effects, then there actually is a accumulating zero frequency offset that occurs over some time scale. And then the full waveform, both this memory plus this zero mean part, would look something like this from a typical system like this 150914 event. So as you can see, it leads to a relatively small offset at late times. And one can ask the question, is the signal, this additional part of the signal here, strong enough that LIGO could actually measure it? And the way to do this is with this sort of signal to noise statistic that I introduced earlier in the talk. So this signal to noise statistic is what's plotted here. So the red lines are contours of constant signal to noise for different total masses of the binary at different distances. And to give you a sense of where the detections have taken place so far, these yellow stars here show, the 10 or so nearest by events that have been detected by LIGO and Virgo. So as you can see, the signal to noise for these events is less than about 0.3 and typically somewhere around 0.1. So that would be something on the order of, like a 0.1 sigma significant detection, if one were to see it, which, is nowhere near a confident detection by most people's standards. So it looks unlikely that one would actually be able to detect this memory effect from individual sources. But what one can do is look for the cumulative effect of many memory detections in a population. So this was an idea from a few years ago by Paul Lasky and collaborators. And he had the idea to look for the total signal to noise in a population. So this total signal to noise generally grows like the square root of the number of events. And he made sort of an optimistic forecast of how many events, just like the first event, this 150914 event, it would take to actually discover the gravitational wave memory effect in this population. And what he found, how to interpret this plot, is basically after about 30 detections of these 150914-like events, one would have, say, a 3 sigma significant detection of the effect. And after, say, 70, then it would rise to about a 5 sigma significant detection. Unfortunately, this is a bit optimistic. So this used a sort of one event and assumed the entire population was like this event. Both a master's student, Albert Boersma, and a collaborator, Patricia Schmidt, we repeated their calculation and looked at how long it would take to accumulate a 3 sigma significant detection in the advanced LIGO and Virgo detectors at their design sensitivity, using a realistic population. So that was consistent with the astrophysical population that LIGO and Virgo has inferred from their detections. And what we found is that it actually takes more like several years or thousands of detections to produce this level of statistical significance that one would need to claim a detection of the memory effect. So it's something that's possible that LIGO and Virgo could do, but it's a bit more challenging than had been initially forecast. So I'll just briefly mention that a sort of different approach has been done by Hübner and collaborators, in which they've found that, in which they've, say, taken the actual gravitational wave events and done a hypothesis test. So computing this evidence ratio or Bayes factor for the hypothesis that the gravitational waves have memory versus they have no memory effect. And they found that the Bayes factor in favor of there being memory is quite small, so nowhere near, say, the log 10 of this being 2 needed to claim a significant detection. But the fact that in the first 40 or so events, there's a Bayes factor this small is consistent with what one would expect from the forecasts of that we've made of the gravitational wave memory effect. Okay, so I see I'm going a bit slower than I intended. So let me just, I think probably the last thing that I'll say is, since this memory effect seems to be quite challenging to detect, what is it that one would learn from detecting it, and why is it so exciting? I think in some sense you've heard some of this from some of the earlier talks in the summer school, but I'll just briefly review the connection between memory and asymptotic symmetries, and why this is something that's worth pursuing, despite the fact that it will take time and will be challenging. So as you, I think, heard in several talks, the asymptotic symmetry group of spacetimes that become flat in the limit as you go to infinity is not the Poincare group, but is the so-called Bondi-Metzner-Sachs group, in which the group is expanded instead of there being just 4 space-time translations. There's an infinite dimensional group of super translations, which are symmetries of the space-time. And in the standard BMS picture, there's a set of 6 Lorentz symmetries, which are the set of global transformations of these 2-sphere cross sections of null infinity. So one can sort of look at schematically what these translations versus super translations do to the space-time, or due to these cuts of constant retarded time at null infinity. And essentially, if you visualize the effect of these super translations in Minkowski space, the standard translations essentially just shift the vertex of a light cone in Minkowski space, either in time or in space. But these super translations, which lead to a highly distorted 2-sphere cross section compared to this initial one, these are the ones that sort of disrupt the light cone or the vertex of the light cone in Minkowski space. They're often not considered to be symmetries of Minkowski space where one wants to preserve this, but in asymptotically flat space-times when one doesn't have this interior, then they're perfectly valid symmetries, and there's no reason to get rid of them. So as you probably learned, associated with every symmetry, there's a corresponding conserved quantity. Several of these are familiar. The ones I've listed here, that energy is related to time translations, rotations, angular momentum, etc. There's, of course, the Lorentz boost, which part of the Poincare group, but have a less familiar conserved quantity, this so-called center of mass angular momentum. What's quite exciting about these larger symmetries is that the supertranslations lead to an infinite set of additional conserved quantities, which are the so-called supermomenta. And when I say conserved here, what I mean is that when you have this picture of null infinity, gravitational waves can change your charges, but the change in the charges is equal to some net flux of energy or linear momentum or supermomentum between the two different retarded times. So this schematic formula that I put up before is just the conservation law for supermomentum. So in other words, the fact that I was computing the strain from these changes in conserved quantities and a certain kind of flux is just the statement of the supermomentum balance law, that these changes in the charges have a part that's that one might call hard, related to massless fields and gravitational waves of non-zero frequency, but this leads to this DC offset, the zero frequency change that's required to have this supermomentum conservation. So in other words, this memory effect is related to the supermomentum balance law, and it's actually required for supermomentum to be conserved in asymptotically flat spacetimes. So I think the main excitement about trying to detect the gravitational wave memory effect is that it shows many things, one of which is that the gravitational waves themselves, they radiate and produce these secondary very low frequency gravitational waves. This supermomentum conservation actually applies to actual astrophysical systems in our universe, like binary black holes. And then I think most interestingly, one nice property of this is that the different vacuum states, the initial and final rest frames of the system, they're not the same. They're super translated, and the memory is precisely telling you what the necessary super translation is to relate the initial and final vacuum states before and after this binary black hole merges. So it is really a quite interesting observational probe that tells one about the asymptotic and infrared structure of space-time. So I think in the interest of time, I'll sort of skip ahead and not discuss some of the future directions, but I'll just move to my conclusions. So, what I've aimed to show through this talk is that, first of all, just remind you that these gravitational wave detectors, they're observing a few binary black hole mergers a week, and this number of detections is only going to increase and provide stronger constraints and so on, as the detector's sensitivities improve. The mergers of binary black holes have confirmed the predictions of GR, in some cases to quite high precision, like these tests of the graviton mass and speed of propagation of gravitational waves, and in other cases, less well, that we can actually distinguish between spin 1 and spin 2 particles with the detectors. So, there's a number of interesting constraints, and there are a number of interesting areas to improve. And then as for the gravitational wave memory effect, so this is an interesting, challenging measurement for LIGO and Virgo that can be done in the future. It will probably take many years of detections before there's actually some sort of statistical evidence for this effect in the population of mergers. And what I didn't get to cover is sort of the future prospects, what future gravitational wave detectors will be able to do in terms of detecting the memory. But the punchline is that they'll be able to detect it with reasonably high signal to noise. We'll actually be able to study it with higher precision. So on that note, I'll stop here, and I'm happy, of course, to answer any questions that you might have.
Thanks a lot, David, for the amazing talk. Are there any questions? So there is a question in the chat. What kind of quantum gravity effects can be measured with gravitational waves? Okay.
Yeah, so I'd say the main things are these things like, that I discussed, is there a graviton mass? That would be some quantum gravitational effect. Are there, what is the spin of the gravitons? That would be from the polarization measurements. And then, is there dispersion or, other sort of dispersive effects? So these are, the tests that are underway. And then, one can phrase this memory effect in terms of a purely classical language, or as you probably saw from Professor Strominger's talk, one can think of this memory effect as part of an infrared triangle. So there's a connection between memory effects, these symmetries, BMS symmetries, and these soft theorems in quantum gravity. So one can think of the memory effect as probing aspects of the low frequency or infrared limit of gravitational wave scattering. So these are what I consider to be the kinds of quantum gravity effects that one can detect. But there's lots of interesting ideas that people have put out there. So for example, one of them is, suppose your black hole horizon, instead of being perfectly transparent, has some small reflectivity due to some quantum mechanical effects. So if it actually slightly reflects gravitational waves, one would have some additional gravitational waves that have scattered off the horizon and then follow after some short time scale. And at least for a time, people found some very tentative evidence that there might be these so-called echoes. So due to the fact that the horizon has some slight reflectivity. Unfortunately, this effect has gone away with more detections, and it looked like it was just sort of some random noise fluctuation. But if you come up with some interesting ideas that produce a macroscopic effect, so something that is on the scale that gravitational waves can measure, then I think there's a lot of interesting possibilities. But I don't think gravitational waves will probe anything directly on the Planck scale, right? I just don't think that the dimensionality lines up that these are macroscopic objects, and Planck scale is whatever 10 to the 40 orders of magnitude smaller than the kind of scales that are being probed by gravitational waves.
Thanks a lot. Florian, I'm going to and allow you to get unmuted.
Sorry.
Yeah, you should be able to ask your question.
Hello, hi. Thank you for the talk. It was very interesting. So in the plots you provided regarding the GR check, the experimental checks, it seemed that all the results were kind of aligned. There was this line except the lunar experiment about the experiment trying to measure the distance with the moon. Is there a way to probe GR? I mean, first, is that a coincidence? And the second question is there a way to probe GR away from this kind of line? Yeah.
Right. Yeah. So you're referring to this plot here.
Yeah.
Yeah. I mean, so most of these systems are binary systems in circular orbits. So yeah, it's not a coincidence that basically as you move to smaller separations, the curvature scale that you're plotting, this is to be expected. So this lunar laser ranging, yeah, I'm trying to think why this is sort of off of this line. I'd have to think a little bit more about why this is the case, but yeah. So for example, one can probe things, for example, in this region. So for example, if you had supermassive binary black hole mergers, these are strongly gravitating, but the mass scale of these systems is 10 to the 6 solar masses, which corresponds to millions of kilometers. So you can probe things in this region of parameter space. I mean, you can also probe short wavelengths and weak gravitational fields up here. So there are non-astrophysical systems, for example, that one can probe just through terrestrial kinds of measurements and so on up here. So there are other regions of this parameter space that one can indeed probe.
Thanks. There is another question by Monica. So Monica, I'm going to give you the opportunity to unmute yourself. If you prefer, I can read your question. Oops, sorry. Yeah, you're muted now, but you should be able to.
Hello?
Yeah. We can
Thank
hear
you. So you mentioned that maybe at some point we will be able of measuring more or knowing more about the stochastic background. Do you know any characteristics or ways in which we could eventually distinguish between astrophysical stochastic gravitational waves and primordial gravitational waves?
Yes, so that will be possible. So for example, if you look at what the spectrum, I don't have a slide for this, but if you look at what the spectrum is for astrophysical sources, it tends to be what people might say is red tilted. So it goes up at lower frequencies, at least up to some point, whereas a primordial spectrum tends to be flat. So in principle, people think about doing this, that you could, if you measure gravitational waves at many different frequencies and you're able to fit the astrophysical background, you could, in principle, subtract it off and go after the primordial part, which would likely have a different frequency dependence than the astrophysical backgrounds. And there are proposed experiments to do this. So most of these are space-based gravitational wave detectors. So I didn't describe these in the talk, but things like LISA may be able to do this depending on how large the cosmological background is. But there are other more advanced detectors, such as the Big Bang Explorer, where they really try, one of the main scientific goals of these instruments is to essentially do this subtraction of the astrophysical background and go after the primordial background. So it is indeed something that can be done, but it's not likely to be done by LIGO just because the anticipated cosmological backgrounds, unless there's something quite interesting or some fun surprises lurking, these are expected to be much lower than what LIGO is capable of measuring. But it's something that future gravitational waves detectors, will be pursuing if these missions are built and so on.
Okay, thank you very much.
Yeah, you're welcome.
Thanks. Any more questions? Okay, so let's thanks David again. Thanks a lot.
Yeah, again, thank you for the invitation.